So first, thank you very much for inviting me here. It's really a pleasure for me. So I will change, as you said, with the focus of what we have been talking these two previous excellent talk, and I will focus my presentation on the use of these organic radicals for molecular electronics. So my name is Nuria Crivillers, and I'm coming from the Institute of Material Science from Barcelona. So maybe I don't have to now, after these two talks, mention what is an organic radical, but briefly molecules that have an ampere electron, and they are quite reactive, and they lose very easily the open shell character. But you can follow at least two strategies to make them stable. One is the screening the paramagnetic center with bulky substituents, or by increasing the localization of the ampere electron over a large part of the atomic skeleton. Following these two strategies, there are few radicals that have been reported in literature, so they can be handled in air and at room temperature. So this has facilitated to employ them in different fields, like, for example, in organic radical batteries. Also, from the more fundamental point of view, in molecular spintronics. Also in biological and biomedical applications, for example, it's the case of this dendrimer that is functionalized with organic radicals. And I don't have to mention, because we had already like these two excellent talks before, the optical properties that they offer are also very, very appealing. So in our group, we have been working for years with this PTM radical that has been already introduced before. So what it makes this radical very stable is these chlorine atoms in the ortho position of this phenyl ring. These bulky chlorine atoms are the ones that are shielding the central carbon atom, that is the one holding the ampere electron. So thanks to this functionalization, this radical is very stable. So it's a neutral radical, and the spin density is strongly localized in this central carbon atom. What makes them very, very interesting is that they show different properties, so they are multifunctional radicals. They are paramagnetic, they are also electrochemically active. So one can reduce the PTM radical to the anion form, and also you can oxidize it to the cation form. They show these interesting optical properties we saw before. And also the fact that they are thermally and chemically very stable, allows the possibility to functionalize them and introduce different groups in different positions of these radicals. So this is what we allowed us to work with these radicals on different type of surfaces. That is what I'm going to explain now. So basically, in the last decade, I would say, we have been put a lot of effort to transfer the properties we knew from solution, to move it towards the surface, with the idea to implement and to try to exploit them in electronic devices or electrical devices. So for example, just let me show some examples here. We have investigated these radicals, once forming self-assembled monolayer on conducting electrodes as a molecular wires. In this work here, it was a clear demonstration that having this SOMO electronic configuration made this radical more conductive if we compare it with a protonated non-radical molecule. And also we have scaled down these devices, and in collaboration with Gerre van der Zaan, we have investigated these radicals in single molecule junctions. Also, we have exploited electrochemical and optical properties for molecular switches, for memories. So we tuned the optical properties by an external electrical input. We have been working on transparent substrate to exploit the optical properties, like in this case with indium tin oxide, but also we have worked on carbon-based substrates to open a bit the applicability of these materials. As well, these are molecules that have been covalently bind to different type of electrodes, but also we have been working on the investigation of the supramolecular organization of the radicals on surfaces. So today, I would like to give a brief overview of some of our results based on these three examples I'm showing here on the right. So let me start with an example of our work in single molecule junctions. So this was first evidence that these radicals could be embedded in a single molecule junction that thanks to observation of this Kondo feature, so it was proof that the radical was in between these two electrodes. So this was our first work. And after that, what we thought that we could improve, or we could try to improve the performance of these junctions, mainly the reproducibility and the stability. So we thought to change the anchoring group. In this work here, we use this thiophene. But of course, it's very and widely known that the group that you use to anchor the molecule on the surface can change the robustness, the stability. You can modulate and decrease the level misalignment, and of course, try to improve and decrease the contact resistance. So based on some works, we thought to use the terminal alkene because this can form sigma bonded carbon gold junctions. And this we decided to explore these groups because this bond is highly directional and also brings a higher hybridization with a metal. And also because it can form a spontaneous bond with gold. So there is no need of adding an extra agent, for example, a base to the protect. So we thought that this could be an excellent group to explore. So also because these terminal alkenes can give a higher chemical versatility, which I would not enter in here because there is a talk from Alejandro de Souza later, so that he will explain much more on this. So this is what we did. So for exploring these terminal alkenes as a new group for forming these single molecule junctions, we synthesized this molecule here. As you can see, it has two terminal alkene groups, and we compared with the ones we reported before that has this thiophene. So all this work we've done in collaboration with Gerrit van der Zaan in the Netherlands. So is the setup, this is the setup we used. That is this mechanically controlled break junction in here. So we use that to explore our systems. So these are room temperature measurements done with this molecule with this terminal alkene. So in this 2D conductance versus electrode displacement graph, what we can see is that there are quite a lot of traces, the ones I'm showing here, that corresponds when there is no molecule reaching the electrodes, so the conductance drop abruptly. But what we see is that there is a clear plateau here, which corresponds when the molecule are reaching the electrodes. Interestingly from here is that if we see a single trace that is represented in here, we see that there is only a peak corresponding to one single conductance value, that is roughly an average value of this conductance that we measure here. Then also, interestingly, you can measure the length of this plateau that is related when the bridge is broken, and is around 2.7 nanometers. That is corresponding more or less to the length of the molecule. So this is already an indication of how the strength of this bridge. If we compare it with this thiophene terminated molecule, what we see already is that we observe different different conductance values. So we have a higher conductance value and a low conductance value here. And that also the junction breaks when we have elongated and separated the electrodes at 0.95 nanometers. That is much less of the length of the molecule. So we wanted to know a bit more why. So we had already the idea that is because of the higher stability of the linking groups. But we did some DFT calculations in here. So what we did was to calculate the maximum rupture force and also the bond dissociation energy using these model systems here. So for the carbon gold bond and the thiophene sulfur gold bond. So what we see that these values are much higher for the carbon gold bond. So this is in agreement with what we observed it. As well as when we did conductance simulation, this was interesting to see, because what we found is that in the case of using the molecule with a terminal alkene, the configurations the different configurations we investigated always lead to this similar configuration, the one I'm showing here. And we didn't see variations between configurations. So, and this is in agreement what we observed experimentally. But in the case of using the molecule with a thiophene, what we observed is that there were different configurations that were possible. So for example, when the junction was simulated using a more flat gold, the molecule had a little interaction with a radical. This is translated with a lower electronic coupling with electrode. So this could lead a lower conductance that we measured. On the contrary, for example, when we use corrugated surface, this corrugated surface induced the formation of this covalent bond. So that means that we increase here the electronic coupling between the molecule and the electrode, and this could lead to the higher conductance that we measured. So this it proved that there is, using these terminal alkenes, we had less variability in conductance, which we believe is a signature of a stronger carbon gold bond with a more stable and well-defined anchoring geometry. On the contrary, when we investigated these molecules with the thiophene, we saw that the conductance we measured were more spread, and also that this could be a signature of the weaker sulfur gold bond with an ill-defined molecular metal contacts. So with that, I would like to move to the second example, that is the functionalization of carbon-based substrates. So before choosing before doing the synthesis of the molecule, of course, so we look in literature, which are the different anchoring groups that we could use. And among the different ones, we choose the free radical addition, that what we needed was to incorporate a diazonium salt in our group, in our PTM radical. So this is the synthesis we follow very briefly. So we needed to go through this derivative that has this triazine protecting group, because we could not do the synthesis of the radical directly on the diazonium derivative, because are not stable under the conditions we use to generate the radical. But upon the formation of the radical with this triazine, it was easily to form the triazine derivative. So we had this PTM radical modified with diazonium salt. So with that, this is the scheme that this is what we wanted and we expected. So the idea is that we reduce the diazonium salt and we form this aryl radical in here. That is the one that is reacting later with a carbon substrate. So we first thought that maybe this intermediate would not be stable, but luckily it was, and we could functionalize the carbon substrate. So in this case, we use HOPG as a model substrate. So the way we did it, so this reaction I'm showing here can take place spontaneously, but also one can, let's say, trigger this reaction by electrochemistry. So one can, by electrochemical means, reduce this salt, and then form this aryl radical in the solution, and this radical interacts with the surface that we are using in this case as a working electrode. So this is what we did. So this is the peak corresponding to the reduction of the salt. As you can see, this peak reduces upon we do several cycles. So this means that this diazonium salt is reacting with our substrate. Once the substrate is rinsed, we can do the cyclic voltammetry of this modified HOPG. And what we see here is a clear signature of the redox process that is taking place between the radical and an ion. So this already indicated that we succeed in functionalizing this carbon substrate. And this also is very stable, so one can perform several cycles and there is no loss of the intensity of the carbon measured. So we wanted to go a bit further and we wanted to measure also the, let's say, the transport in this type of substrates. And for that, we use electrochemical scanning tunneling microscopy. We did it in collaboration with Alexander Ratnev in the University of Bern. So this is a scheme of what we have in our setup. So we have our HOPG substrate modified with our radicals. We use a gold STM tip. This is immersed in an electrolyte, and then we can switch the redox state of our radical and measure the tunneling current between the tip and the substrate. So this is the cyclic voltammetry acquired with this setup. We clearly show that still in this setup, we see the redox process corresponding to the radical. So this is what we observe. So the first thing to say here is that using the concentration, low concentration that we use of the radical, we observe that mainly the step H's were functionalized and very little radicals were observed on the basal plane of the carbon substrate. So once we observed that, we could, let's say, play with and modify the redox of the radicals that are attached on these step H's, and this is what we did. So this is a scheme of the, let's say, the cyclic voltammetry, what we see, and this is the position of the bias that we apply. So if we measure on one side of the redox wave or in the other, what we observe is that we see a change here on the brightness of the STM. And taking into consideration that these images were recorded in a constant current mode, so this difference in the cross-section profile, so we see an increase of the apparent height here and this brightness, this increase in the brightness of the images in the STM. It means that we are modifying and increasing the tunneling current that we are measuring between the STM tip and the substrate. So let's say here that the conclusion is here that we could modify the HOP substrate, and that by tuning the redox of the touch radical, we could tune the tunneling that we measure between the tip and the substrate. So one could say here that these PTM radicals attached to the carbon substrate display a transistor-like functionality under electrochemical conditions. So, and to finish my presentation, I would like to show this last example that here we don't attach the molecules in a covalent manner, but we physisorb it on a surface. So here, we investigated not the PTM radical, but the TTM that we already saw in the previous talk. The difference with the PTM radical is that only the ortho and the para positions are having these chlorine atoms, but also this TTM radical is highly stable. So because it's highly stable, because it's highly stable, we can thermally evaporate it on different substrates. And this is what we did. So we use gold, platinum, and graphene. And our idea is that we want to explore these films as organic memories. And our idea came from a previously reported work in which they used this organic radical in here. So a film of this radical was embedded in two gold electrodes, and they observed a very nice memory behavior. So, but what we thought, since we had the technique here in our lab, is to use, instead of evaporating a gold or a metallic top electrode, which sometimes it can lead to the penetration of some metallic atoms into the organic film. So what we thought is to use this liquid metal as a top electrode with idea to, because this can permit to have some soft contact with the organic layer. So with the idea to avoid this penetration of this possible penetration of the top electrode into the organic film, and then make sure that what we observe is really coming from the organic film. So the first thing we did was to investigate the self-assembly of this TTM radical on these different substrates. So gold and platinum was very similar, and I'm showing here only the ones obtained on gold. So what we saw first is that when we thermally evaporated this TTM radical on gold, if we keep the gold at room temperature, these dendritic type of structures were formed. But if we played with the temperature of the substrate during the evaporation, we could reach the formation of this very homogeneous film at when we kept the substrate at 60 degrees. And this is an AFM image of the substrate in which the roughness is very low. Completely different is what we observed with graphene, that when we evaporated this TTM radical on graphene, transferred on quartz, we saw these fibrillar-like structures, evidencing here that in this case, when the TTM is evaporated on this type of substrates, the molecule-molecule interaction prevails in compared with the molecule-substrate interaction. So because of this, we could not investigate electrically this film. We cannot characterize it electrically, because we had a very high irreproducibility of this, but we could measure the transport through this film using the ones deposited on gold and platinum. So we sandwiched this, just to mention that we did the UPS of these films to corroborate that the radical character was maintained after the evaporation, and it was, so we confirmed that. So we embedded this TTM radical film between the gold and platinum and our liquid metal top electrode. So this is the AB curve that we recorded. So comparing the gold and platinum, they are quite similar. So this is, sorry, I didn't mention that it's a 20 nanometer thick film. The thing is that we saw a slight difference on the rectification. So it seems that the film, when it is deposited on gold, it shows a higher rectification. That means that the current at the positive bias is higher than the one we measured in the negative bias. So we attributed this to the different injection barrier. Here again, what we already saw with the self-assembled monolayers. So the difference in the energetic barrier between the Fermi level of the metal and the SUMO is here playing a role. So taking into account that the work function of the gold and the platinum is different. So this is what is leading here the difference in the rectification. But what we were looking for is this memory effect. And this, we didn't observe it in this voltage range. So we did this to increase the voltage range that we apply. And this is a typical curve that we obtain. So what we see in the negative parts, we observe this hysteretic behavior here, that it was attributed to the charging and discharging process of the TTM radical. So this is assigned to the redox, of the tuning of the redox of the radical that is embedded in between the two electrodes. And we obtain a maximum on-off current between the two states over 100. That is already quite significant. So to finish, I hope that I could show you how the chemical stability of the radicals permitted to functionalize with different anchoring groups, and then allowed us to integrate them in different type of devices. We explore gold, carbon, as well as on thin films. So, and very recently, thanks to this nice way of functionalizing carbon, let's say, very stable and very efficient. So in collaboration with Jana Samswell, we just reported the functionalization of carbon nanotubes. And we investigated the interaction of these luminescent effects with these carbon radicals. So I would like to finish just thanking all the people involved in this work, all the people from ICMA, and as well our collaboration and our funding agencies. And thank you for your attention.